Alright, this lecture is going to be on lenses. We're going to be looking at how light is transmitted and refracted. Here's a couple different examples of topics we've looked at up to this point. So here we have a laser being shined into some material. It's going to refract. Here we have light that we see clearly a stripe that is, or stripes on the wall behind this glass of water, and it's being distorted. And lastly, light that's reflecting off of object X and Y and how we see it at a little different location, say if we're looking into water. So they all apply to lenses here in refraction. The two types of lenses we're going to look at are concave and convex lenses. Concave lenses diverge light, spreads it away, refracts it away. Convex lenses converge light, moves it towards. Let's watch this little video clip.
In this video, we're going to look at both concave and convex lenses. Notice that a lens allows for light or photons to pass straight through. But if I move towards a concave lens, notice the greater the amount of concaveness is, the greater that light refracts. And notice that it bends outward. It bends outward because it's refracting as it moves through the concave lens. That if I have a convex lens, it's going to be converging. So notice the convergence, I'm changing the location of the focus. So here I have the changing of my focus with convex. Once again, they converge. Convex converges, and concave diverges. Diverges means moves away. So I have divergence here.
So we're really looking at lenses and refraction. So a converging lens bends the rays inward toward the focal point. Notice light travels in straight lines. It's going to bend through the media, through a different medium, and it's going to reach at this point. But I want you to pay attention here that this light ray continues traveling in a straight line. And this line keeps traveling in a straight line here. So converging creates a focal point. A diverging lens bends the rays outward, away from the focal point. So I'm trying to re-emphasize this, and you'll see a lot of pictures that are showing the same picture. I want to pay attention to this ray right here. Notice it's going to refract. We'll look at this a little closer here in just a few moments. Notice that this ray diverges. If I retrace it back, the focal point is on the side in which the light is coming from. That all of these rays point to where the focal point is located. So let's look at what we did in class. Convex lenses. Observe the beams of light. There are 4 beams of light here that are refracting to the focus where they converge together. They are on the other side of the lens. In the picture below, the light traveling through the center of the lens continues traveling in a straight line. So notice this detail. This is kind of an interesting one. This keeps on traveling through the focus. This is the center of curvature. In this case, it just keeps traveling in a straight line. But anything that hits it at a point of the curvature is going to refract. So we see them continuing right after passing through the focus. Observe the light continuing in a straight line. So I've shown you this a couple times. I just want you to see that it continues traveling even beyond the focal point. So concave lenses, where we see diverging light, sometimes they're called diverging lenses. Light is spread out from the focus. So notice, here's my concave lens. Here's the light. It's going to travel through here. It's going to refract. It's going to bend away. The focal point here, if we trace this back, the focal point would be kind of somewhere in here. You can essentially just rewind all these points, and where they all intersect is the focus, or the focal point of a concave lens. So images that we look at through a concave lens are always virtual. They're located on the front of the lens, the same side as the object, and they're formed in our minds. They're right side up, and they're smaller. So why does light diverge traveling through a concave lens? Well, all rules of refraction apply here. Observe the incident ray traveling from air with an n value of 1.0001 into glass with an n value of 1.5. Notice air to glass. Well, we have some rules here. The rules are that if it travels from a low n value to a high n value, notice what's going to happen to my ray here. Pay attention here, it's a curved surface. Here's my normal line that's perpendicular to the surface. The incident ray, as measured from the normal line, is going to be greater than the refracted ray. Here's why. N value from low to high is going to refract towards the normal line. So notice, this angle is going to be larger than this. It's bent towards the normal line. It's the refraction, right, as it slows down. It's going to travel in a straight line as it's transmitted through the glass. At this point here, here's my incident ray, always measured from the normal line. It's going to refract away from, it goes from high to low, it's going to refract away from this normal line. Remember, we're working with curved surfaces here, so everything changes, particularly the normal line. So here's kind of the explanation of that, but sometimes it's just worth looking at the picture here. So just as what happened here, or the same thing's going to happen to the ray down here. It's going to go from low to high. It's going to refract towards the normal line. Remember, the normal line is drawn relative to the surface. It is curved here. It's going to continue traveling straight. It's going to refract away from the normal line, going from high to low. Hopefully that makes sense. So why does light converge traveling through a convex lens? Well, same rules apply. We're going from air into glass. Notice my angle of incidence here of my incident ray itself. This angle is larger because the surface here is curved. So my normal line is perpendicular to the surface. This ray is going to refract or bend towards the normal line, going from low to high. It's going to bend towards. Continues being transmitted through. Curved surface again, perpendicular to it. It is going to then refract here. Here's my incident ray. Here's my refracted ray. It's going to bend or refract away from the normal line. And it's going to reach the focal point. And the same rules apply here. Low to high, it's going to bend towards. High to low, at this normal, it's going to refract away from the normal line. So incident rays here that travel parallel to the principal axis will refract through the lens and converge to a point, and that's our focal point. This slide has a lot of words on it, but I'm just going to summarize the picture. The refraction rules for converging lens and refraction rules for diverging lens. We'll do converging first. So any incident ray traveling parallel to the principal axis of a converging lens will refract through the lens and travel through the focal point on the opposite side. So this will refract, travel through the focus. This will refract, travel through the focus. If we had a light ray traveling here, it would actually travel straight through. There's no angle for it to refract to. So in this case, all rays will pass through this particular focal point. So here, if I look at it for diverging lens, any incident ray traveling parallel to the principal axis of the diverging lens will refract through the lens and travel in line with the focal point. In other words, here's your focal point. So this is going to refract. It's going to refract through here. It's going to travel this direction. So I could retrace this line or extend it to the focal point. Same with this ray here. It's going to refract. It's going to diverge. If I retrace this back, it's going to travel through the focal point. So let's apply lens types to vision. So convex lenses, they converge light to a focal point or a focus. The human eyeball lens is a convex lens. Convex lenses are used for people who are farsighted. It changes where the focus is located so that it reaches your retina, where your photoreceptors. Remember, your photoreceptors contain cones, rods, and cones. Cones for color, rods for intensity. This is what interprets the light. In a concave lens, these diverge light. The focal point is on the lens side, or in this case, where the light's coming from. Concave lenses for people who are nearsighted, changing the focus to reach the retina. So here's some common eye defects showing the handling of parallel input rays as if from a very distant object. And this is just showing that, in this case here, farsighted, it travels too far. Nearsighted, it doesn't travel far enough. When I say it, I'm saying where the light is going to be focused on your retina. And astigmatism simply just puts them in all kinds of different locations. So we'll look at these a little further. So farsighted in corrective lenses. If the eyeball is too short, a converging or convex lens can be used to correct the condition. The lens refracts the light entering the eye to focus it on the retina. So here we can see it's too far, right? This isn't focused on the retina, so this would be a blurry vision. So if you have correction, you put a lens on here, contact lens, glasses, even surgery to have this repaired. Farsightedness can be corrected by, in this case, we can look at converging lenses. So light refracts before reaching the cornea and is subsequently focused on the retina, and that's where you want it to be. And for nearsighted, right, correcting nearsightedness, the eyeball is too long. So a diverging or concave lens can be used to correct the condition. Here we see the lens refracts away from the principal axis before then enters the eye, and then the rays are able to focus on the retina. So you're simply changing this location, you're moving it back so that it reaches the image reaches the retina, and the image is simply the light. And lastly, astigmatism. It simply is just the eyeball's cornea is misshapen. This is a defect in the eye or the lens caused by a deviation from the spherical curvature. In other words, there's something funky going on. It's got some misshape to it, which results in a distorted image. If we look at this picture, it enters the misshapen cornea, it changes the way light goes through the lens, and you get light scattered across the retina. And you can notice that you want all this light focused on the retina, not in multiple locations. So the light rays are prevented from meeting at a common focus, and that's essentially what astigmatism is.